right, good morning, everybody. Thank you for joining us. I see a whole bunch of people are joining in our waiting room, so we'll get those folks entered in stride as we go along. So I'm super excited today. I want to say welcome to our first webinar of 2023. Today we're going to be discussing synchronous generator and utility paralleling modes of operation. Like I said earlier, this is our first webinar of 2023. If you are a returning viewer, welcome back and Happy New Year to you. And if you're new to our webinars, thank you for joining us. It really means a lot to us that you've taken time out of your day to join us for this webinar. Just a little bit about Enercon Engineering. So Enercon is a power system integration solutions expert. Our products are engineered to meet customer specifications and requirements. Our main facility is located in East Peoria, Illinois. That's where we do all our design, manufacturing, and testing. And we've done over 40,000 projects, not only domestically, but around the globe and about 110 different countries. I'm your host, Sean Lott. I am the Vice President of Global Sales. Before we jump into the actual presentation itself, I want to tell you how you can interact with us, because this is an interactive webinar. So all you need to do is up in your toolbar, go ahead and click the Q&A tab, the question and answer tab. And when that opens up, you can enter your questions. Once your questions are entered, just hit the submit button, and then we will see it. We will moderate the questions. We're not going to ask the questions in stride during the presentation, but we'll ask them at the end as time allows. If for some reason we didn't get to your question, I apologize for that up front if we run out of time, but we will have all the questions answered and send it out to all of the attendees on the webinar upon conclusion of the actual webinar itself. Now, I'm happy to introduce our guest speaker. He is one of our gems, Steve Conrad. Steve is from Springfield, Illinois. He attended DeVry Technology in the late 60s. He worked for companies like Singamo and Simplex. At Simplex, Steve had his first exposure to power generations and controls, where he manufactured control panels, voltage regulators, diesel day fuel tanks, and switchgear from 1972 to 1977. He moved on to CAT for 3 years in Kentucky before he joined Enercon in 1981. At Enercon, Steve has served as the testing technician, the field technician, where he provided services in over 47 countries. He then was a project design engineer and an engineering manager. Currently, Steve is our senior applications engineer. Steve did retire from Enercon 10 years ago, but he still provides part-time expertise to us on a daily basis, and we are certainly thankful for that. So without further ado, let me welcome our guest speaker to the stage, Steve. And Steve, go ahead and unmute yourself.
Okay.
All right, we got you loud and clear. How are you doing?
I'm doing just fine.
All right, so I'm going to exit stage left and let Steve take control. All right, Steve, the floor is yours.
Okay, thank you very much, Sean, and welcome all. And I hope you get something out of this presentation that we've put together. We're going to talk about paralleling modes and how we control the generators. First of all, let's look at some of the criteria. The utility, we always normally refer to this as, the normal source, the mains, or the grid. But more importantly, it is considered an infinite source when we parallel the generators. And that is because when we parallel generators to the utility, we absolutely cannot influence frequency. The utility is going to dictate what that frequency is. And for the most part, it is exactly 60.0. The frequency in this country is extremely stable. So we can't change that. Same with the voltage. There can be minor voltage influences, but that's basically only due to transformers. As we load and unload transformers, there may be some minor fluctuations, but for the most part, the generator's not going to influence that. And how we do this is the generator and utility, we have controllers that control how the generators load and unload, and how the utilities react. We do this by biasing the speed to the generators. Basically, speed will control the kW output. We also bias the voltage regulators, which controls the kVARs and the power output, the power factor. Anytime we parallel generators to the utility, we have to control the kW and the power factor. And I'll give you an example of what we're talking about here. As I said earlier, the frequency is exactly 60 hertz in this country. Today's engines are very well regulated as far as the speed and the voltage. The governors on these engines, the engines today, of course, they're for the most part all electronic. The governors are very accurate. So when you set the speed, it's typically 0.25% regulated. So if we don't control the speed bias, what will happen is, for example, let's say that we parallel a generator and the generator is running at 60.1 hertz. The utility is going to bring it to 60. And if the speed signal set point is at 60.1, then it's going to try to go to 60.1. Utility is going to have it locked, so it'll continue to increase the fuel to try to maintain or get to that set point. And what will result is eventually it'll go into overload. Converse to that, if the speed was, say, set at 59.9, utility is going to keep it at 60. The electronic governor is going to continue to reduce fuel to try to bring it back to the set point of 59.9, which eventually is going to result in reverse power. And the same thing is going to happen with the voltage regulator. It's going to either overexcite or underexcite. So it's very important that we control the speed and the excitation on the generator. So when we're operating in base load, selling kilowatts back to the utility, usually they're going to want to see a high power factor so that they don't have a bunch of bars going into their system. When we go to import or zero power transfer modes, we usually want to try and match the power factor on the generator to match the site load. And I've got an illustration here. Let's look at the very top, and this is without generation. So our facility is consuming 1,000 kilowatts, 750 kVARs, which results in a 0.8 power factor that's lagging. And of course, the utility is contributing to that entire load because we don't have generators online. So in the middle, when the generator is not set properly, we've set the power factor on that generator to 0.91 lagging. And then look what happens. Our load is still the same, but look at the utility contribution. We've reduced the kilowatts down to 500. The generator is producing 500. But because of that power factor not set correctly, the utility is only contributing 525 kVARs. The generator is contributing 225, and there's our 0.91 power factor on the generator. But look what happened to the utility. Its power factor is down to 0.69, and utility, they don't like to see low power factors like that. So they will pretty much force you to set the power factor where it should be. And there at the bottom is basically the proper setting. We've told the generator to produce 0.8 power factor. And if you look at all the contribution below, the load's still the same. The utility and the generator have equal kW and equal kVAR contribution to the loads. So the power factor on both remain at 0.8. So again, just wanted to stress the importance of power factor settings. The rest of the presentation, when we go into the illustrations and that, I'm just going to talk about kilowatts. So just assume that the power factor settings are correct for all these illustrations. Okay, let's talk about the modes of operation. First, I'm just going to touch briefly on momentary paralleling versus soft load, soft unload. And then the operating modes, we're going to talk about base load. We're going to talk about import control. And we're going to talk about ZPT, or zero power transfer. Some people refer to this as storm anticipation. And at the end, I want to touch on plant islanding, what happens when we've got generators online and there's a utility failure. Momentary paralleling. Usually this is just used for closed transition back to utility after we've had an outage. And this transfer can be done with automatic transfer switches. Usually closed transition is an option. Or we can do this with what we call transfer breaker pairs, meaning we'll have a breaker on the utility and we'll have a breaker on the generator. Generally, most utilities, if it's momentary paralleling, they don't want more than 100 millisecond parallel time. And that's usually the utility's limitation. And that requires fewer components because we don't need any load controls or anything like that. Usually less protective relaying is required because, again, we're only going to stay in parallel no more than 100 milliseconds. And there's generally a lot more wear on the breaker contacts, basically because we're closing and opening breakers under load. And there's more power surges to the utility and the generator. Obviously, the utility can absorb surges much better than the generator can, but we just, in 100 milliseconds, we don't have time basically to control the power flow from the generator and the utility. Soft load, soft line load. This is the extended parallel time. Sometimes some applications, generators stay in parallel 24/7. We can control the rate of how fast we load and unload the generators by settings within the controller. A lot of this also pertains to or is affected by engine performance. All engines don't load and unload at the same rates. You've got various generator sizes and things like that, engine characteristics that are affected. Generally, we're going to require more components. We're going to have load controllers, not only for the generator, but some applications we have controllers on the utility as well. And usually we're going to have more relay protection required, just for the simple fact that the generators will stay in parallel with the utility for extended periods of time. And it will definitely extend the contact life of the breaker, because we're typically, unless it's a fault condition that happens under normal operation, we're never going to close the breaker we're always going to close the breaker practically with no load, whether we open or close breakers, whether it be the utility breaker, the generator breaker. And there will be little or no power surges between the utility and the generator. And that's because we don't have any kW output from the generator until we tell it to start to increase or decrease its output. Base load. Base loading is just, we put a constant kW output on the generator. When we go into base load mode, we really don't need to necessarily monitor how much power we're putting into the utility. The only thing that we're trying to do is just to control a constant generator output. Import control, basically, we're going to try to do a constant level from the utility. We're going to control how much power we're going to bring into the facility. So as loads change, we're going to change the generator output so that we can maintain this constant import level, which will be a set point. And zero power transfer, basically it's a means of soft transferring the loads from the utility to the generator and back. Zero power transfer initially starts out as import control. And then we bring it completely to zero from the utility. And then we go on to generator power and then go back. And we've got illustrations for these modes. And again, the base loading generator is going to produce a constant kW output, regardless of the utility or parasitic loads. And what we mean by parasitic loads, these are the loads that's at the facility. And probably the best example for base loading would be landfill applications, where they recover the landfill gas and use that as fuel in the generators. The parasitic loads would be the site loads. You've got radiator fan motors, you've got fuel treatment skids that's got pumps and things, and you've got lighting and heating and ventilation. Those are your parasitic loads. So as those loads fluctuate, the generators still are going to produce a constant kW output into the or out of the grid. And as again, probably the most common use is landfill generation. If the utility will not allow, in certain applications, the utility does not want any power fed back into their grid, and if you're going to base load the generator, then you've got to be sure that your connected load is greater than the generator output, because the generator output's going to offset your connected load first. And if your connected load's less than your output, then you are going to backfeed into the utility. And not all applications will the utility allow that. And the nice thing about base loading, if you're able to, it does make a good means of load testing the generator without having to use a load bank. Gas turbines, they're very most commonly used with base loading, since they use heat recovery. Gas turbines typically don't like varying loads. And here's a graph that I put together, and you'll have to excuse my cursor here. As we start out here, as you notice the load in blue, that's the load profile. The generator output in red, and you notice that's constant. It's always going to put out 500 kW. That's where our set point is. And then down below in green is the utility contribution. So as we start here on the far left there, we start out, the load is only 400 kW. We're generating 500 kW. So the result is that we're actually putting 100 kW back into the grid. So then at this point here, the load is exactly what the generator is doing. So we're not importing or exporting load or kW into the utility. So in this area here, where our load is greater than the generator output, the deficit is made up by the utility. And then this area here, where the load is less than generator output, the excess is fed back into the utility, and so forth. So this is base load. And again, it's a constant generator output. Now let's look here at an illustration. You see we have a factory here, and presently the factory's load is 2000 kW. We're going to set a base load set point of 3000 kilowatts, 3 megawatts. And we initiate base load operation. We signal the generator to start. Generator synchronizes, closes the breaker, And again, at the moment that breaker closes, there's very little or no current flowing through the breaker. And so initially we start out at 0 kW. We're going to start increasing the output of the generator. And as we increase the output of the generator, the imported utility kW will start to reduce. Our facility load has stayed the same, it's 2,000. So the utility kW and the generator kW will always total to equal what the load is. And we load up to 3,000 kW. Now our load's only 2,000. So we're actually pushing 1,000 kilowatts back into the utility. And of course we would be, that would generate revenue because we're selling kW. And now our facility load decreased. It dropped 500 kW down to 15. We're still producing 3,000. We're still base loading. And we're exporting now 1,500 kW. And this is where some people get confused. Even though we're exporting, we're not export control. The reason we're exporting various amounts is because of the load variations at our facility. But again, we're exporting power, but it's not export control. And we terminate the base load operation. Our plant load is down at 2,500 kW. We're unloading the generator. And when the generator gets down to near 0 kW, we open the generator breaker. Engine runs for a cool down period and shuts down. The utility is back to supplying our total facility load. Now let's talk about import control. We also refer to this as peak shaving or load following. It's used for utility load curtailment contracts. A lot of times the utility sometimes, especially in the summer, a lot of them need more power than they can generate. So they will look for customers that have on-site generation. They will sign curtailment contracts. And basically that says that the utility is allowed to call them so many times a year. Usually it's a number of times, maybe a certain number of hours, and tell them to put your generators online, start loading up to a set point, and run until we tell you to remove your generation from the utility. And here's a chart of import control. We have essentially a utility set point of 100 kilowatts. So as our load fluctuates up and down, our generator output also fluctuates up and down, so that it's always 100 kilowatts less than the load. So the utility, we're always going to import 100 kW. Now, if there's minor surges and fluctuations, pump startup and things like that, generator cannot respond instantly to load surges like the utility. But over average, we maintain this solid output. There has been some applications where the utility will want you to have your utility import level set point at 0. So a lot of people would ask the question, well, if you're going to bring your utility to 0, why don't you just open the utility breaker and run on generator? But by continue to be in parallel with the utility, it definitely gives you frequency stability. So again, as motors come on and generate the surge required, the utility will absorb that surge. So you still are going to maintain a very, very solid frequency. You're not going to have many frequency excursions at all due to surges. So that's the advantage of staying in parallel with the utility. All right, here's import control. Here's our facility. Its load is 4,000 kW. And we're gonna initiate import control. And let's say that our import level set point is 500 kW. So we initiate it, the generator signal to start, generator comes up, synchronizes with the utility, closes its breaker. We're now in parallel with the utility. And again, when that utility breaker closed, there was very little or no current flow through the breaker until we start to load. So now we're loading the generator up. Generator is producing 500 kW. Our utility is importing 3,500. And remember, our set point on the utility import was 500 kW. We continue to increase the output of the generator until the utility is at 500 kW, and that's the import set point. Now, all of a sudden, if you noticed, look what our building load, the load increased instantaneously. The utility is going to absorb that surge because I cannot increase the generator output as fast as the load increased. So what we do then is the load control sees that, starts to increase the output of the generator until that utility import set point of 500 kW is reduced, and now the utility is back at its import level set point. So that's import control. And again, as the building load increases and decreases, we increase and decrease the output of the generator to maintain that import level setting, a set point, whatever it may be. So when we get done to terminate, all we do is start to unload the generator, and which shifts the load onto the utility. We continue to decrease the output of the generator. When it gets down to near 0 kW, we open the generator breaker. And again, very little current flow through the breaker. And then we run the engine in a cool down period and shut down. And that's basically how import control works. Now we're going to talk about zero power transfer. And again, this is a way to soft transfer the load from the generator to the utility in a very slow, controlled rate of loading and rate of unloading. Common mode for this, data centers, other critical load networks. In the past, we've done switchgear for, say, data centers, for example, that have actually monitored storm activity. So rather than to take the risk of having to go through an outage, they would choose to go ahead and go onto their generators, disconnect from the utility until the storm anticipation has passed. They also will call it storm avoidance sometimes. Now this graph, I must admit, it's not a very good graph, only because I show the load as a very, very constant. But basically, what we're doing here at point A is when we put the generator online, and as it loads, the utility unloads. When we get to B, utility's at 0, we open the utility breaker. So the time period from B to C is when we're strictly on generator power. At C, we resync back to the utility, close the utility breaker, and then as we start to unload the generator, we shift that load back to the utility. And when we get to D, then time period, then the generator will trip offline and shut down. And I've got an illustration for this. Here again, we're going to initiate the zero power transfer. Genset is started. Generator synchronizes to the utility, and we close the generator breaker. And again, anytime the utility breaker is closed and the generator breaker is closed, we have control of not only the KW, but we're also controlling the excitation and we're controlling the power factor, as we mentioned during the first part of this presentation. So now that we've got the generator breaker closed, we're going to start loading the generator. And as the generator output increases, imported utility KW decreases. And again, you can see that this basically is the same as import control, other than we're going to force the utility to zero. And once we get that utility near zero, we're going to open the utility breaker. So when the utility breaker opens, very little or no current flowing through it. We've already reduced all the KW and the K bars. And now we're totally on generator power. So if there's a utility outage or a utility disturbance, it doesn't matter. We're isolated, we're on the generator, just as if we would be in a standby mode. So when we terminate the zero power transfer, storm activity is passed. They feel comfortable to go back to the utility. So we actually synchronize the generator, even though it's loaded. We synchronize the generator back to the utility. Utility breaker closes. Instantly, there's no power flow from the utility until we tell the generator to start to unload. So we start unloading that generator, which causes the power to shift over to the utility. We'll continue to decrease the generator output until the output is near zero. When it's down to that, we will shut the generator breaker. Generator goes into cool down and shuts down. Utility islanding. Utility islanding basically is a condition that occurs if there's a utility failure or disturbance, and we've still got the site generation in parallel with the utility. And it's usually caused by a reclosure opening due to a fault, lightning, down power lines, or whatever. Could be a minor utility failure, or it could be a very catastrophic utility failure. Protective relaying is what we use to detect this condition. And we open the main incoming breaker so that we can isolate this facility and continue to operate on generator. And with proper logic and control, as I just said, we can design this so that it'll instantly go into standby operation automatically. So we won't have a disturbance to the load. It will continue to remain powered by the emergency generator system. And due to this, due to the distance, these reclosures, they're basically utility switches that have overcurrent built into them. And we don't monitor the position of these switches by our load controls. A lot of these reclosures may be half a mile or greater. So it's really not practical to be able to take auxiliary contacts into the system to monitor that. It's just almost impossible to do. So again, when the utility reclosure opens, we don't know that it's open. So the generator load control, it's still active. It still thinks that it's in parallel with utility. Technically, it's in parallel, but there is no utility. And the load control is still going to try to maintain the KW and power factor that was set, but utility is not there to absorb any of this generation. So the result is the KW online is greater than the generator capacity, you're more than less very quickly going to overload that generator, probably go under voltage or under frequency very quick. And the same thing that can also occur with the voltage. So that's probably the first thing that's going to happen is you're going to have a very quick frequency change from the generator. And sometimes, depending on the system and where the generator is located, we can have over or under frequency, but we will have a frequency disturbance, and also we can have an over under voltage occur due to we're still controlling the excitation on the generator. The protective relaying reacts to this abnormal voltage and or frequency, and we'll use this relaying to trip the main utility breaker at our site, thus isolating the generator from the utility, which of course has failed. And I want to say something about the reclosure, the timing. A reclosure, most reclosures in this country, most utilities have the reclosure set for about 3 different reclosures. So what happens is usually the first reclosure is very instant, usually no more than a second. And I'm sure you've all been at home in the evening watching TV and storms going on outside, and all of a sudden your lights go out. About a half a second or a second later, they come back on. And they may stay on. Well, what happens is there probably was a lightning strike on the line, created an overcurrent, reclosure opened, the lightning strike dissipates, the fault clears, reclosure recloses, and everybody's happy again. Now, if the fault still exists, the reclosure will open up again. And then it will reclose, and usually the second reclosure timing is longer than the first one. So, for example, if a tree had fallen across the line, then the fault's going to continue to be there. So the reclosure will open the second time and wait a little bit longer than the second reclosure, and it'll reclose for the third time. Now, most utilities have the reclosure set for 3 reclosings, and then it's a lockout. So if, like I said, if it's a tree that's fallen across the line, after the third reclosing, it's going to lock out because that fault's not going to go away. So a lot of times, the reclosure times will have to be coordinated with the utility, because we have to be able to have enough time in that reclosure to allow us to clear. We need to be able to, and if you notice next to this utility breaker, there's a protective relay. So usually that time has to, we have time in our relaying. The relaying will pick up a lockout relay. The lockout relay will in turn open that utility breaker. So this time has to be coordinated with the utility reclosure. And generally, utilities will coordinate that. They may have to, for example, if their first reclosing time is set at a half a second, they may have to set that to 1 second. And they will coordinate those times with the customers. So as you can see, in this case, we have a lightning strike on the line, and then that creates an overcurrent fault. And then if you notice down on the line, here's our full reclosure. So that reclosure is going to open. And when that reclosure opens, remember, our generator doesn't know that. Our generator still thinks that it's in parallel with utility. So it's going to try to maintain whatever kilowatt loads and power factor settings that was set, but the utility is not there to absorb it. So what happens is, as the protective relaying detects this voltage and or frequency abnormality, it will issue a trip signal to that generator breaker, or I mean the utility breaker. So once that utility breaker opens, then the generator is isolated. And as soon as that generator is isolated, because the load controls do monitor the utility breaker. So by opening the utility breaker, we now know that we are isolated from the utility. And we can instantly go into a standby or emergency operation. And at that point, we would disable the load controls. The governor will maintain speed, frequency, and the generator voltage regulator will maintain whatever the program voltage was. Now, once the utility does return, we will resync the generator if we're still wanting to remain in operation in parallel with utility. We would just resync to the utility, close the utility breaker, and then go back into whatever mode, import mode or base load or whatever. And you also notice that on this grid, there's other loads. There's a couple of other factories. So when that reclosure opens, our generator is going to try to also support the load on those other factories, which generally, as I had said earlier, you're going to go down on frequency very, very rapidly, which again, that protective relay will sense that, open the utility breaker, and isolate the other loads that are on that portion of the grid, and allow us to stay online with the generator and operate in the standby mode. Okay, that kind of does it. This is basically what we had just discussed. We've gone over the criteria, talked about the momentary and soft load, talked about the modes of operation, base load, import, CPT, and we touched on generator plant islanding. And are there any questions? That's Sean.
Yeah, I'm getting there. Here we go. All right, there you go. I'm on the screen now. So yeah, thanks, Steve, for a very, very, very good, informative rundown. Learned a lot. We don't have many questions in the Q&A, but there's still time to ask. So again, feel free to like click that Q&A tab so you can ask your questions so we can get your questions answered. It's anonymous, by the way, so I'm not going to like say, Joe Smedlap submitted this question and so on and so forth. So it's non-attributional. So, if you feel like your question is not that tight of a question, don't feel embarrassed by it. It's not going to be shared, but we'll definitely get those questions answered. So as we wait, I'll just give it a couple of minutes here, Steve. So one question I do have for you, and these are questions from me, is what are the limitations of zero power transfer?
Well, I mean, I'm not sure exactly what you mean by limitations, but obviously you're not going to be able to do zero power transfer. You're not going to be able to transfer the entire load, obviously, unless your generation has the capacity to do such. You got to be sure that your generators, whether it be one generator or multiple generator, the capacity at least has to be able to fully pick up the entire connected load.
Okay. All right. Thank you. And here's a question. And you touched on this a little bit. I think relays is part of the answer here. But what are the effects of the utility islanding on the power grid itself?
Well, actually, once the generator gets isolated, of course, then it's totally running by itself. So there's really, I mean, when the utility fails, once we clear, and usually the time delays in the relays, usually the frequency settings, whether it be under frequency or over frequency, that relatively is going to have a very, very short time delay, because again, once we stay in parallel with utility, it's 60 hertz. So typically your under frequency setting, it's probably going to be as close as like 59.5. Your over frequency may be set tight as well, probably like 60.5 with a very, very short time delay, because again, we have to be sure we get offline real quick before reclosures start reclosing. And as soon as we can react and open that utility breaker, then essentially we have no influence on the utility until we reparallel, resynchronize back and resume operation in parallel with utility.
Okay. All right. Here's a question in from the chat. Can you move your mouse there real quick? I think you right clicked on something there. Anyway, I'll ask the question. I'm not sure why that's popping up. There you go. So is there a time associated for the transfer of utility to generator? Is it like in seconds, milliseconds? Is there a time standard associated with that?
Yeah, that's a good question. And basically, this is why we refer to this as soft load, soft unload. The actual amount of time is pretty much, those are the settings that are entered into the controller. So you can control how much time it takes. You can set it at 20 seconds, a minute. But keep in mind, because we're talking about rotating mass and that of the engine generators, specifically the engines, for example, let's say we've got a 1 megawatt generator. You're not going to load that 1 megawatt generator in 2 or 3 seconds. We're talking more like 10 seconds, 15 seconds. It does have the limitations, but for the most part, I'd say within 10, 15, 20 seconds, we could probably load it, unload the utility, and converse going back after we go back to the utility, we could probably unload it in maybe 15, 20, 25 seconds. You're not going to be able to unload it instantaneously unless you open the breaker. Of course, if you open the breaker, that defeats the whole purpose of soft unloading. But that's probably typically what you're looking at, maybe, 15, 20, 25 seconds. Going from no load to full load and back.
Okay. So the next question is, how are microgrid controls different from what was just discussed?
Well, microgrid controls, there you're getting involved with a lot more control. You're getting involved with wind and PVC solar cells. That's just a whole separate entity in itself as far as the controls, which definitely gets a lot more involved than what we're talking about here. Although the generation, the controls certainly can be integrated with microgrid control systems, definitely. That's a whole nother topic of discussion.
Yeah, we'll table that one and write that one down. That would probably be a good topic to
yes
have a discussion on.
Yeah.
Okay, so the next question that came in is, what type of relay and what relay function do you typically use to provide utility islanding protection?
Okay, and a lot of times, there's many protective relay manufacturers out there. Utilities are always going to require what the industry refers to as utility grade. There's less accurate, less expensive, what we call industrial grade protective relays, but utilities won't allow that. It's got to be a utility grade relay. There's many manufacturers, but typically probably, and again, some of the times the utility will will require additional protective functions, if you will. The most common would be over in the voltage, over in the frequency, probably with very, very short time delays. You know, depending on the system, sometimes the utility may require distance relaying, you know. We've been involved with that, but probably over under frequency, over under voltage by far is the most common. You know, of course, those relays will also have overcurrent functions built into them. You know, sometimes you may require differential relaying and transfers. It's pretty much dependent on site conditions and utility requirements, basically.
Okay. All right. The next question it deals with basically the reliability of the gear. So, how long does paralleling gear last?
Wow, that's a good question. Well, probably the number one, as we'll say, wear and tear, obviously is going to be the circuit breakers. That's moving parts. That's the things that absorb the surges, the currents as we open and close. You know, that's probably your number one. The rest of the components, I would say, as far as longevity, boy, that's a difficult question. One thing that we are running into now is retrofits because we find that a lot of the components that we put in switchgear that's 20 years old, a lot of these components, even though they haven't failed or anything, a lot of them are just obsolete. You can't get them. You know, I'll use, for example, PLC components. You know, you have a PLC that's 20 years old. You can't buy you have a bad output card. You can't find it. We've even heard of customers actually going on to eBay to get an obsolete module, if you will. So I would say probably the time period, it's all other than the breakers. I would say the time period for the most part, it just has to do with component obsolescence. Yeah, interesting question.
Yeah, and I would also too say that too, if you don't know what kind of components you have or the age of your gear, you could probably have somebody come in and just do an assessment and just give you a good rundown on what it is that we see from an expert perspective, and then make recommendations and go from there and make sure your stuff is as up to date as possible and reliable as possible, and to extend the life of the gear as well too. So, next question deals with communication. So what type of external communications is available for building automations? So for example, Modbus, Cobra, TCP/IP.
Yeah, well, and of course, over the years, you know, the communications have really improved. You know, like for example, Modbus has been around for, well, I don't know how long, but definitely a long time. We still find a lot of devices that communicate over Modbus. The controller technology, you know, when we talk about the controllers that are necessary for this type of operation, that technology has also really increased. Most of the controllers now, you know, will communicate with Modbus. A lot of the intercommunications between the controllers, a lot of that is done over what we call CAN bus, controller area network. So CAN bus is very popular, and Ethernet. Almost all of the devices now communicate over Ethernet, which makes it very, very easy to integrate these controllers for monitoring and things like that. A lot of these are very easily integrated into building automation systems and SCADA systems and things like that, just because of the availability of the communications.
Okay. And I think we're going to have time to squeeze in one more question. And I do know we were leaving some of the questions on the table, but like I said before, we'll get these questions answered, and we'll send those answers to those questions out to the audience, so they know they get our take and our input to those questions. So this one deals with emissions. So can you comment on the effect that newer emissions regulations have had on the use of base loading, peak shaving, storm avoidance, et cetera? And we're talking about in the continental United States.
Well, I'm certainly no expert on that. However, I do know, over the years, EPA has changed requirements. The engines have gone through many iterations of what they call tier levels. And yeah, years ago, as far as what you put a generator online compared to today is definitely much different. Some of the gen sets now, they're into tier 4. They're into the pollutions that are produced are definitely very, very sensitive to EPA in that, and tier 4 engines now mostly are required. If you have a legacy type engine generator set, you probably may not be able to use it for extended periods of time for base loading and things like that. Yeah, definitely.
All right, Steve. Well, thank you so much for your time. Again, you're one of our treasures within the company. You're the third most tenured employee that we have, and we really appreciate your time and your effort to package this for us and put everything together. And if you have any additional questions, feel free to reach out and contact us.
Yes.
Yeah, and we'll see what we can do to help you out. There's two things I want to share with you real quick. One of which is, I hope you guys can see that there, but it is our webpage. So if you go the YouTube page, so on the YouTube page itself, it has all of our videos, webinar videos and company videos on there. So if you go to YouTube and in the chat bar up here, not chat bar, in the search tool, you put in @Enercon Power and just hit enter, and it'll bring you right to our page, and you can see all the videos and things of that nature. This video will also is being recorded, and once it gets cleaned up, we'll get this one posted as well. So you can go back and look at it or share it with your team members, however you see fit. Also, I want to bring to your attention, because some folks may not know this, but we have launched a full-blown formal blog that we kick out on a monthly basis. So if you go to our webpage at enerconpower.com/blog, and I'll put this in the chat as well, you will see that there are a whole bunch of blogs here that you can go through and read at your own leisure. And if you have anything that you would want to know about, that you asked a question, that also may generate a blog topic for us or a webinar topic as well. So just want to bring that to your attention. So with that, I want to thank everybody again for attending. Spring is like right around the corner, so I'm sure everybody's looking forward to getting out there in the yard and doing some yard work and seeing some flowers and things of that nature, and enjoying some really nice weather. And thank you for your time and your participation. And we
Yes,
will.
and I'd like to thank everybody as well, Sean. Thank you very much.
All right. All right, guys. Well, as our founder would say, Ed Tangle, let's get back to work.